Okay, good morning. Let's go ahead and begin. Okay, we're gonna jump into 16.2. 16.1 was basically for you guys to read on your own. The basic premise of that whole chapter is just to inform you of what a vector field is. It's really not too tough. It's just giving you what the vector would be at any given xy value. And that's really all you really need to take away from 16.1 is that, you know, at every single xy value in the plane, there's going to be a specific vector that's associated with that, and that's going to, you know, model for us fluid flow and fluid dynamics and, you know, yeah, anything where you have water or air or anything that can move together but separately at the same time. So the whole item is moving together, but the individual units and the individual parts are moving separately. Okay, so we're going to build up to how we deal with vector fields, but we needed some tools to help get us there. And one of those tools that helps us get there is something called a line integral. So let's jump into what a line integral, and I'm going to put the line in quotation marks because it's really not a line. It really should be called a curve integral. Okay, it's really a curved line and not just a straight line. Okay, so in Calc 2, we defined arc length given by parametric equations as, okay, and depending upon who your Calc 2 teacher was, depends on whether or not you've seen this formula. Don't freak out, it's the same formula that we've been dealing with before, okay, just in parametric form. Okay, so this is L equals, okay, a to b of the square root of dx dt squared plus dy dt squared. Okay, so it's just taking the x component of the parameter and taking the derivative of that, squaring it, okay, plus the y component of the parameter, taking the derivative of that, squaring it, adding it together, and finding the distance between those two by taking the square root. Okay, and that's going to obviously be integrated with respect to t. Okay, integrating over a curve C gives us something called a line integral. Okay, line integral. Okay, and again, it's really should be called a curve integral because that's really what it is. It's a curve integral. Okay, you know, how did we find, you know, arc length? Well, we're not finding necessarily arc length of a line. We're finding arc length of a curve. Okay, a line is just a special curve. Okay, and it's just, they called it a line integral instead of a curve integral. It's fine. Okay, because they think about like drawing Okay, a line on a piece of paper. You could draw a curved line, I suppose. Okay, you could curve that line. So anyway, just think about it as a curve. Okay, a two-dimensional curve. Okay, two dims, right? Okay. Okay, so I have a couple of pictures of this. I'm gonna draw the first one here because I know I can draw that one. The second one I'm going to attempt to draw, and I may fail miserably, but we'll see how it works out. Okay, so here's the first one. Okay, so say I have a curve like so. Okay, this is a curve in the XY plane. Okay, and I call this curve C. Okay, C for curve. I know it's, you know, it's real obvious why we call that C, right? Okay, so I have a curve in the XY plane, and I'm going to integrate over this curve, right? That would give me my curve length, or what we would call our arc length. But in this case, I'm going to integrate over Z, okay? I'm going to integrate over Z, okay? And so we call that ds. And what this creates is this creates a two-dimensional surface that I'm actually integrating over. Now the Z coordinate, maybe I'll do something like so. Okay, but maybe I'll do something like this. Okay, it doesn't necessarily have to follow the same height. Okay, they don't have to be parallel. Okay, think of it like a, you know, waving flag or something. I don't know, a pennant. Think of it as like a pennant. Okay, if you know what a pennant is, that's okay. And so again, this is kind of a horizontal. I know it's kind of hard to visualize. This is a horizontal curve C, but it's a vertical surface. It's a vertical surface. Okay. And so we're summing up C. We're summing up C, which is the curve, but then we're extending that in the third dimension in the Z direction. Okay, given some parameter, maybe that parameter is a plane, or maybe that parameter is another, okay, is another surface. Okay, but the idea, okay, is that we only go up a certain height, and that height is bounded by some sort of function, okay, of x and y, right? And that would be Z. Does that make sense? Hopefully it'll make more sense as we go along. Okay. The other picture that I have a little bit harder to draw. This is if I had it in this was the Z direction. This was the X direction, the Y direction. Now the curve is really easy to draw here, right? Because it's in the XY plane. So the curve is incredibly easy to draw. We could draw something like that, okay? But then when I go out here, okay, it becomes a little bit more challenging. Okay, and then what's my surface gonna look like? Well, it's gonna look like this. Okay, and kind of again, think of kind of a flag waving in the wind. This time the flag is horizontal instead of vertical. Okay, So, and then what's C in this case? What's the curve? The curve C, that would be this one. Maybe I should use a different color. Maybe I'll just highlight it. Okay, this one right here is curve C. Okay, so that is my curve C in the XY plane. Now we immediately translate the function in XY into T. We have to parameterize this in terms of T, one variable. Otherwise, we end up having to do double and triple integrals, which are not fun. Okay, and we want to leave those for something else. Okay. Okay, so the idea here is that, okay, we want to integrate over a curve C of Z, f of xy, and then this is going to be, okay, over that curve, right? Over that curve. Okay. So the curve, though, was, in order to get the arc length of that curve, okay, curve C, that was dx dt squared plus dy dt squared. Okay, and so the only minor change that I would want to change to this is I would want to emphasize that f of x of t and y of t, these must be, x's and y's must be in terms of t, a third variable t, and then this is dt. Okay, so make that bigger. Okay, and so this is how we get something called a line integral. Okay, line integral. Okay. Okay, so let's jump into an example. Number one, evaluate. Okay, the line integral on C. Okay, think of C as my domain in my x and y region. Okay, what can x and y be? Well, it's that domain is going to be defined by a function. Okay, C of 2 plus x squared y. Okay, and then we're going to go ds. ds is the curve. Okay, it's over that curve. Okay, curve C. Okay, where C is the upper half of the unit circle. Okay. Okay, so let's set this up, right? Looking at our function. Okay, so first we need to parameterize this. So what's the parametric form of the unit circle? Right, we have to get x and y in terms of a third variable t here. Well, we already know how to parameterize the circle. It's called polar coordinates. Okay, and so I'm going to say that x is equal to cosine of t and y is equal to sine of t. Okay, so x is equal to cosine t, y is equal to sine of t. Okay, cool. Now, what does the function or the equation look like to get my line integral? Well, it's the integral over c, so we've got to figure out what is happening over c here, okay, to get my limits of integration. And then we're going to do f of x of t. Okay, so well, what is f of x of t, y of t? Well, that's this function 2 plus x squared y. So this is 2 plus, okay, x of t, but what is x in respect to t? Well, isn't that cosine of t or cosine squared t? right? What about y? Well, y is, it's times y, so y is sine t. Okay, so that's kind of cool. This is going to make a nice integration, one nice little u sub on cosine. Okay, let's take the square root of dx dt. Well, what's dx dt? Well, that's just x prime, right? X prime of t. Well, what is x prime? Well, that's negative sine t, right? And then, so x prime, again, going back to the formula here, okay, that's dx dt is x prime is negative sine t, and I'm going to put the squared on the outside just to emphasize that that negative gets squared, okay, becomes positive. Okay, and then what's the derivative of y? Well, y prime is equal to cosine of t, and that becomes plus cosine squared t. And that's really nice because this negative cosine t squared plus the, negative sine t squared plus the cosine squared t, that just becomes sine squared plus cosine squared, which we know is 1. This thing all equals 1. The square root of 1 is 1, and so this thing basically goes away. Okay, this is going to be over dt. Now all I have to do is figure out my limits of integration. Well, this says that this thing is going to be over the half circle, okay, from the upper half circle, right? So upper half circle. So where would I start and where would I end? Well, again, think of t as theta, right? T is equal to theta here. Okay, think of t as theta. Well, where is theta going from in the upper half of the circle here? Well, isn't theta going from 0 to pi? Right, isn't it starting here? If we were to draw us traveling along this curve, wouldn't we travel along this half circle and we'd be going from 0 to pi? Well, yeah, we would. So 0 to pi of, this is going to be 2 plus cosine squared t sine t dt. Okay. Where did the square root go? Again, that's the square root of 1. It's a really nice problem, and it just goes away. Okay, just gets multiplied out. Okay, let's look at a u sub here. Let's do u is equal to cosine of t, right? U sub on this thing. U is equal to cosine of t. Okay, that means that du, well, we already saw that what that was negative sine t, right? And so negative du is equal to negative du is equal to sine t dt. Okay, and so this is going to be, okay, the integral 0 to pi. I'm going to break this up into two integrals because I'm using a u sub on the second one here. Okay, 0 to pi of 2 plus, that should be 2 dt, plus, okay, using my u sub that I have here, that's going to be the integral from, now I can either transfer my limits of integration now, or I can turn it back into t's at the very end, you know, undo my substitution and then leave it as 0 to pi. I'm going to transfer my limits of integration now. Okay, so I'm going to say that u of 0 is equal to 1, and u of pi is equal to negative 1. So this really is going from 1 to negative 1 of u squared. Okay. Okay, so this one's real simple. Evaluating this one, this becomes 2t evaluated from 0 to pi, okay, which just becomes 2 pi. Okay. Okay, and then what's this one going to become? This is, again, a really easy one. This is 1/3 u cubed, okay, from 1 to negative 1. Okay. Okay, just making sure I did that correctly. Did I make an error somewhere? Oh, I did. I forgot to put in the negative for the du. Negative du. There we go. Okay. So yeah, that was my error. I forgot to put in the negative du because this should be a negative. Okay. Okay. So now let's plug in our limits of integration here. This is going to be plug in -1. The two negatives cancel. I'm left with 1/3. Okay, and then this is going to be minus, plug in the 1, minus a -1/3. This is going to be 1/3 plus 1/3. So this is 2 pi plus 2/3. Okay. Okay, any questions about number 1 here? Okay. Okay, let's go on to number 2. Okay, evaluate. Okay, the line integral over C of 2x ds. Okay, 2x ds. Now that ds implies that this is a line integral. Okay, it's not dx. Okay, it's ds. It's a line integral. Okay, where C consists of the arc C1, okay, of the parabola okay, y equals x squared from 0, 0 to 1, 1, and C2, there's going to be two pieces to my line integral. I'm going to take them each independently. Okay, C2 and C2 of the line x equals 1, I guess I should say the line x equals 1 from 1, 1 to 1, 2. Okay. Okay. So what is this thing going to look like? Well, we have a parabola, okay, or a piece of parabola that goes like that. Okay, from 0, 0 to 1, 1, right? Okay, so that's my parabola, my piece of parabola. Okay, 0, 0 to 1, 1. And then what happens here is I go vertical. Okay, from 1, 1 to 1, 2. So this is 1, 1. That's 1, 2. Okay, goes from 1, 1 to 1, 2. Boom. Okay, so we have a vertical line. Okay, this guy is my x squared. This guy is x equals 1. Okay. Okay, so let's take this in pieces. Let's do a line integral on just the first one here. Okay, so we want a line integral, okay, of C1, okay, of C1 of f of x of t, y of t, times the square root of dx dt squared plus dy dt squared dt. Okay, let's do this one for C1 first. Okay, for y equals x squared. Now I need to parameterize, I can never get that word right. Parameterize y equals x squared. Okay, well, for really simple functions like these parent functions, okay, the easiest way to parameterize, is that how you say that? I can't even do it. Okay, parameterize. It's parameterize. I'm looking it up. I'm looking it up. Sorry, I digress. Okay. I want to learn. I want to be educated. I want to be edumacated. Okay, parameterize. Parametrized. I'm looking it up.
Parameterize.
Thank you, dictionary.com.
Parameterize.
Parameterize.
Parameterize. Parameterize.
Thank you. Okay, got it. There we go. Parameterize. Dang. See, there ain't nothing you can't learn on the internet. Okay, parameterize, as that lovely female voice said. Okay, let's parameterize y equals x squared. The easiest way to parameterize y equals x squared is just to let x equal t. We're going to let x equal t. Okay, and then what would that make y? Well, obviously, then y would equal t squared, right? So the easiest way to parameterize this is to let x equal t, and then y just equals t squared, because that's what x was. Okay, so what would be dx dt? Well, that would just be 1. What would be dy dt? Well, that would just be 2t. Okay. Okay. So, and then what's t going from? See, if x is equal to t, then for our segment of parabola, then what is x going? What is t going from? Because we have to have a boundary on t because we're integrating with respect to t, right? We're not integrating with respect to x. We're integrating with respect to t. So what is t going from? Well, if x went from 0 to 1 and x is t, then wouldn't t go from 0 to 1? Right? So t is going to go from 0 to 1. Okay, cool. Cool. Okay, so let's take a look at this. Okay, we want to integrate, we're going to call this C1. Okay, well, we know that we're going to integrate from 0 to 1 because that's what our t is. Okay, this is just the first piece of this. This is my x squared piece. Y equals x squared piece. Okay, from 0 to 1 of 2, what was our function? It was 2x, right? 2, and then what was x? Well, x was t. Okay, 2t, and then we want the square root of dx dt. Well, what was dx dt? Well, that was 1 squared. And then dy dt is going to be 2t squared, okay, dt. Okay, well, this is a nice u sub. Okay, if I were to simplify this, this becomes 1 plus 4t squared. I can do a u of 1 plus 4t squared. I get du equals 8t dt. Okay, I apologize if I'm writing too fast for you to keep up, but okay, du is equal to 8t dt. Well, what do I want? I don't want an 8t dt. I want a 2t dt, right? Now what I want a 2t dt. So what can I do? Well, I can divide by 4. And so I get a du over 4 is equal to 2t dt. Well, there's my integration factor. Okay, 2t dt is my integration factor. So what does this become? This just becomes, okay, 0 to, well, not 0 now. Let's translate our limits of integration. This is going to be 1 to 5 of u to the 1/2. Okay, and then it's du over 4. Okay, I'm going to go over here. Okay, so when I integrate this, this becomes 2/3, right? Times 1/4. Okay, don't forget the 1/4. Maybe I should reverse this. This is 1/4 times 2/3 u to the 3/2 evaluated from 1 to 5. Okay, the 2 and the 4 are going to cancel. Okay, and that's going to be 1/6. Okay, and this is going to be 5 to the 3/2 minus 1 to the 3/2. Okay, so this is 1/6. This is just going to be 5 radical 5. And I'll let you convince yourself of that. Okay, and so this just becomes 5 radical 5 minus 1 over 6. Okay, but that's my first piece. That's just the first part of this, right? All I did was find the line integral for the first part, for C1. Okay, so C1. What I need to now do is find the line integral for C2. Okay, so the second part of my line, or my line in quotes, my curve. Okay, for the second part of my curve, C2, we've got to now parameterize the line x equals 1. Okay, so how are we going to parameterize x equals 1? Well, let's think about this for a second. What are we wanting with x equals 1? Well, we're always wanting x to be equal to 1. Huh. Okay. Well, if x is always 1, then it doesn't matter what y is, right? So we could let x be 1, and then y can be anything that I want it to be. Well, can't we just let that be the variable t? Right, doesn't that make sense? Isn't that really what a vertical line is? It's just 1 comma and then any other value. So that's 1t. Oh, okay. So there's my parametric equation, x equals 1 and y equals t. Okay, that's cool. Well, what's x prime? X prime is 0. What's y prime? Y prime is 1, right? Oh, okay. So, and then what is t going to go from in our equation, right? In our line integral. Well, in this case, y was equal to t, and so what's t going from? Well, t is going from 1 to 2 because that's what y is going from. So t is going from 1 to 2. Okay, just think about it as a particle on traveling on this curve. Okay, and the y's are what's varying, and how are they varying? Well, they're varying from 1 to 2. Okay. Okay, so we have our setup. So integral from C1 of f of x of t, y of t. Okay, and then this is dx dt squared plus dy dt squared dt. Okay. Oops. Okay, so again, what do we want? We want 2 times x, right? That was my original function. Remember, it was not dx, 2x. 2x ds, remember that? That's what I'm doing my line integral over, right? So the 2x is in the z direction. That's the function of x, y. Okay, well, what is x in this case? In this case, x is 1, right? So x is 1, so 2 times 1. Okay, and then what's the line integral going from? Well, it's going from 0. No, sorry, my bad. What's t going from? It's going from 1 to 2. Okay, from 1 to 2. And then the square root of what? Well, it's the square root of x prime squared. Well, what's x prime? It's 0. And then what's y prime squared? It's 1. Okay, dt. So this is kind of nice. This just becomes 1 to 2 of 2 dt. Okay, well, then that just 2t from 1 to 2, right? And then if I plug that in, don't I just get 4 minus 2? And so that's 2. Okay, so let's put these two pieces together. This is going to be 5 radical 5 minus 1 over 6 plus 2. And I can make this the same fraction, one fraction, by just letting this 2, okay, be equal to 12 over 6. And so I get 5 radical 5 minus 11 over 6. And that's my answer. Okay. Okay, I'll let you finish writing that up. I need to go get a bottle of water real quick. I'll be right back. Okay, I'm back. Okay. Actually, I've kind of run out of room. That's a lot of writing we've done so far. Okay, let me insert more blank pages. Okay. There we go. Okay, let's move on to number 3. Okay, a wire takes the shape of the semicircle. You're like, we're doing a lot of semicircle stuff. Yeah, because it's easy. Okay, that's why. Because it's easy, we can actually integrate these. There's somewhere it would take a computer to integrate. Okay, so semicircle. Okay, and you're like, Professor Holman, easy is relative to you. Like, yeah, I guess so. Okay. I guess I should say they're integrable. Okay, yeah, some things are not integrable. So you have to use approximations. y is greater than or equal to 0. Okay, and wire takes the shape of semicircle. Okay, and is thicker near the bottom near the base than near the top. Okay, find the center of mass of the wire if linear density at any point is proportional to its distance from the line y equals 1. Okay. And you're like, what does that mean? How are we going to do this? Okay, well, it's actually not too bad. Okay, so let's first draw the line. Okay, so maybe I'll put let's first draw what we would call an auxiliary line. Again, I cannot talk today. Okay, an auxiliary line, which is this line y equals 1. So I'm going to let 1 equal there. Okay, let me get my ruler here. Okay, let's move that down a little. Then I'm going to do some dashing. Boom. Okay. Let's get rid of the ruler. Okay, so we have our auxiliary line. Okay, y equals 1. Okay. And then the wire itself, I'm going to put in purple. Okay, I'm going to go out here 1, 1. And that wire, okay, is this purple circle, half circle. Okay. Okay, you get the idea. Okay, so that's that wire. Okay, and so it's saying that its density is proportional. Its density is proportional to the distance it is from this line y equals 1. Now, we're going to use a line integral here because we're trying to find the center of mass of this wire. This wire acts like a curve. Okay, the wire does not act like an area. Okay, so whereas we used double integrals, okay, to find the center of mass over an area, okay, we're now going to use you know, a line integral to find the center of mass of this wire. Okay, and so we're proportional to these guys. Okay, proportional from the distance. Okay, so the density, right? So the density we're writing as rho of xy, okay, is proportional. So we need to have a proportionality constant, k, and it's proportional to the distance from the line y equals 1. Well, what's the distance from the wire to the line y equals 1. Okay, well, wouldn't that be 1 minus the y component, right? So wouldn't that be the distance between the line y equals 1 and a point on that, right? So if the y component here was, say, I don't know, 2/3, then wouldn't the distance from the line y equal 1 equal 1 minus 2/3? That makes sense? And then some sort of proportionality constant as well. Okay. So what we're going to be doing here is we're going to say, we're going to do a line integral. A line integral on what? Well, a line integral on rho xy, right? And then the square root of dx dt squared plus dy dt squared dt. Okay. So what is rho? Well, rho is, okay, oh, and why are we doing this line integral to begin with? Okay, what is this going to give us? This is going to give us the mass, right? The mass. That's the total mass of this wire. Okay, and that's what we wanted. We need to use that to find the center of mass, right? We need the mass first, the total mass. That's what we're going to divide by to get the center of mass. Okay, so we have rho of x of y, okay, which is this k times 1 minus y, right? But we need to parametrize this, right? So how are we going to parametrize a half circle? Well, we just did that, okay? We just did the half circle, okay? That was x equals cosine t, y equals sine t, right? So we're going to take this sine t and we're going to plug it in for y. Okay. And then when we did this before, what did we find the derivatives to sum up to when I squared them? Well, wasn't that 1? I don't want to have to do it again, but this is just going to be equal to 1. If that makes sense. So what does this become? Well, this becomes k times 1 minus sine t times negative sine squared plus what negative sine quantity squared plus cosine squared. That's going to equal 1 again. Okay, and then what are we going from? Well, it's from 0 to pi, and that's dt. Okay, makes sense? Okay, I'm going to pull the k out in front. 0 to pi of 1 minus sine t dt. What's this going to be equal to? This is k times t minus or plus cosine t, okay, evaluated from 0 to pi. Okay, so k times, plug in pi plus cosine of pi minus 0 plus cosine of 0. And we get k of pi plus cosine of pi is negative 1 minus 0, that's just 0, plus cosine of 0 is 1. So this is a minus 1. Okay. And so we get k times pi minus 2. Okay, k times pi minus 2. Okay, and so that's the mass. That's the mass. You're like, yay, we're done with the problem. No, we're not even close to being done with the problem. Sorry. Okay. I still got an hour. Okay, baby. This is some good math. Okay. Okay, so this is the mass with respect to some proportionality constant. Okay, so now what do we have to do? Well, we've got to do 2 more integrals. 2 more line integrals. Okay, some good stuff here. Okay, now you want to do the easy one first, or you want to do the hard one first? Well, let's do the easy one first. Let's get that out of the way. Okay, let's do the easy one. The easy one is really x bar in this case. Okay, and what was x bar? It was 1 over m, right? Times, okay, c x rho of xy. Okay, and we're going to do a ds here in this case over this wire. Okay, instead of a dA. Okay. Okay, makes sense. Okay. Or it could be dV if we're doing it over a volume. Okay. We could do a triple integral with respect to the density for a volume. Okay, but in this case, we're just going to do a single integral, okay, using our line integral formula. And we have this 1 over m. Well, what was 1 over m? Well, 1 over m was 1 over k times pi over 2, or pi minus 2, sorry. Okay, so what was x? Well, when we parameterize this, doesn't x become cosine t? Okay, what was this thing here? Okay, what was this thing here? This is just going to be k, right? I mean, remember, well, maybe I'll just write it out. Okay, so this is c, k times x times 1 times k times 1 minus y, right? Remember that? K times 1 minus y ds. Tells me that I'm going to have to do a line integral on these. Okay, I need to, again, parameterize this. I could pull the k out and they would cancel. I'll get 1 over pi minus 2. Okay, and again, when we parameterize this is x equals cosine t and y equals sine t, right? And so what's this thing gonna parameterize to? Okay, well, this thing is just gonna parameterize to x, which is cosine t, times 1 minus sine t, right? Okay, and that's dt. Again, well, I don't want to skip this. Okay, this is times the square root of negative sine squared negative sine t squared plus cosine t squared. But you understand that this thing is just going to equal 1. Okay, but I don't want you to think that we didn't include it. Okay, this ds means that when I parameterize, I have to have that arc length. Okay, this is the arc length function. Okay, now it's dt. Okay, and t is going to go from 0 to pi. Okay. Okay. So what is this going to become? Well, this is 1 over pi minus 2. This is going to be cosine t minus cosine t sine t. Okay. From 0, okay, 0 to pi. Okay. Okay, so let's integrate these. Well, the first one, let me actually break this up into 2 integrals. Okay. Okay, the first one, I'm going to integrate cosine of t. Well, that's super simple. That's just sine t, right? Okay. Sine t, and that's going to be from 0 to pi. So what is that going to become? Well, that's going to be just be 0 minus 0, right? Because what's the sine of 0? 0. What's the sine of pi? 0. That just becomes 0. Okay, that's interesting. Okay, so that goes to zeros. So then I'm left with negative of 0 to pi of cosine sine t. Cosine sine t dt. Okay. So what can I do here? Well, it can do a u sub, right? Which do I want to do? I can't even talk today. Okay, which u is the smartest u to choose? Okay, which u is the smartest u to choose in this case? Well, again, this thing went to 0. Okay, I have this negative outside. It really depends on whether or not I want to get rid of this negative or not, right? If I choose sine, then that'll give me cosine t. If I choose cosine, that'll give me negative sine t. So if I want to cancel out this negative, I might just want to choose cosine, which will give me a negative sine t, right? dt. Okay. Okay, so, and then what's u of 0? U of 0, cosine of 0, that's 1, right? What's u of pi? Well, that's negative 1, right? U of pi is negative 1. Okay. Okay, and so we're going to go from 1 to negative 1. I guess it really didn't matter that I canceled that negative out, but so it's all good. Okay, of u, okay, u du, right? U du. Okay, looks good, looks good. We cancel out the negative. Looks good to me. Okay, so now what are we doing? Okay, so now we're going to get ku, sorry, ku u squared over 2, okay, from 1 to negative 1, right? U squared over 2, 1 to negative 1. Okay, so what does this become? Well, if I plug in my negative 1, I get 1/2. If I plug in my 1, I also get 1/2. And 1/2 minus 1/2 goes to 0. And so we saw that this was 0 plus 0, which is equal to 0. And so that is my x bar. X bar was equal to 0. Now, why does this make sense? Why does it even make sense that my center of mass was equal to 0 in the x direction? Well, because the wire was a semicircle, right? Where do you think the center of mass should be on a semicircle? Wouldn't it be in the middle of the x values, which we have set up as 0 in the middle? Does that make sense? It's kind of like that balancing point, right? It's kind of like if you had a pencil here and you were balancing this wire on this pencil. That's a really bad pencil. But if you were balancing that wire on that pencil, where would that wire balance? Well, wouldn't it balance in the center because of the symmetry involved? Yeah, it would. It would. Okay, so x bar is equal to 0. Okay, so now let's find out what y bar is. Y bar is not as straightforward. You're like, that was straightforward? Yeah, well, yeah. You take what you can get, right? Okay. So y bar is equal to the line integral, right? The line integral with respect to y of rho of xy ds. Okay, so again, I'm not going to do I'm not going to go into a lot of detail on you know, restating things I've already stated. Okay, so what's y? Y is sine t. What is this? This is 1 minus sine t. And then I have a proportionality constant on the outside. Okay, this is going to be the square root of negative sine squared t. I don't even really want to do this. Cosine t squared, that equals 1, goes away. dt, this is going to be equal to k. Okay. Oh, and by the way, for x bar, okay, it is equal to 0. But what we would have to do is we'd have to do it's 1 over m times this times 0. So remember that 1 over m. What was 1 over what was m? M was k times pi minus 2, right? Okay, we canceled out the k's in the beginning. We just got pi 1 over pi minus 2. So this would be 1 over pi minus 2 times 0, which is just 0. Okay, so just keep in mind that you do have to, you know, put the 1 over m. I forgot that on the y bar here. Okay, so this is k over m. Okay, k over m. Okay, what is m? M is k times pi minus 2. Those are going to cancel. I'm going to be left with the 1 over pi minus 2. I just have to multiply by 1 over pi minus 2 at the very end for these. And I forgot to do that on x bar. Okay, but it didn't matter because it was 0 anyway. Okay, and then this becomes sine t minus sine squared t, right? Okay, from 0 to pi dt. Okay. So integrating this, let's break it up into two integrals again. 0 to pi of sine t dt. Okay. Again with the 1 over pi minus 2 on the outside. Okay. Sine t dt. Okay, plus the integral, or sorry, minus the integral from 0 to pi of sine squared t dt. Okay. Equals 1 over pi minus 2. Okay. You think if like an algebra student were to walk in on the session, they would just freak out and like run and turn off their computer as soon as possible. I think so. I think they'd be like, yeah, they would run away in terror. Okay, so they're like, this is one problem. I'm like, yeah, this is one problem. This is fun stuff. Okay, anyway, I digress. It's early in the morning. Okay. Okay. I just feel like, oh my gosh. Okay, so let's keep going. Let's keep moving and grooving. Okay, so what's the integral of sine t? Okay, yeah, negative cosine t, right? Okay, so this is going to be negative cosine t evaluated from 0 to pi. Okay, and what's this thing going to be? The sine squareds. Well, we've seen sine squareds before, right? What are we going to have to do? We're going to have to do our half angle identity. Okay, finally got that one right too. It's the half angle identity for this one, right? Our magical half angles. Okay, so what is that? 1 minus, or 1/2 minus cosine. I'll just do 1/2 cosine 2t, right? dt. I'm just going to write it like that. I'm going to save myself a step. Okay. Okay, so now, when we integrate this, I could do a u sub on 2t. Okay, u equals 2t. du equals 2 dt, so du over 2 equals dt. I could do a u sub on that and then sub it back in. I'm going to do a u sub and then undo the u sub. It just makes it a whole lot easier because then I don't have to break this up again because I don't want to change my limits of integration for the 1/2. So again, I'm going to skip a step here, but it's just for my own sanity. Okay, this is really going to be, okay, integrating this. This is going to be minus 1/2 t. Okay, and then this is going to be minus 1/4 sine of 2t. And if you want to really convince yourself that this is the derivative, just take the derivative of this. Okay, what's the derivative of this? Well, isn't that cosine of 2t with an extra 2? I'll multiply that 2 by 1/4, and what do you get? Well, you get 1/2. So it works. Okay, so we've got that going on there. Okay, we've got our negative cosine t going on there, right? And then the whole thing is evaluated from 0 to pi. Okay. Since I subbed it back as t, okay, if I subbed it back as t without changing my limits of integration, I can just do the whole thing with regard to pi and 0. Okay, so now let's figure out what this is. Okay, distribute our negative sign. We get 1 over pi minus 2. 1, that's an equal sign. 1 over pi minus 2 times, this is going to be, okay, parentheses. I say parentheses, I use a bracket. Bracket, parentheses, negative cosine of pi minus 1/2 pi plus 1/4 sine 2 pi minus negative cosine 0, okay, minus 1/2 of 0, which is just 0, okay, plus 1/4 of sine of 0. Okay, well, what does this clean up to be? This is negative cosine of pi. Well, that's a negative of a negative 1. This is minus 1/2 pi. This is 0. Okay, because sine of 2 pi is 0. Okay, this is negative cosine. This is the negative of a negative cosine of 0. Well, cosine of 0 is, yeah, it's 1, right? Okay, so this is the negative of a negative of a 1. So that's positive 1. Okay, so I just distribute there. This is 0, and this is 0. Those go to 0, those go to 0. Okay, and so we just are left with 1 plus 1, which is 2. This is 2 minus 1/2 pi. Okay, all over pi minus 2. Sometimes you don't really want to have fractions over fractions. So I could multiply both top and bottom by 2 if I really wanted to make it prettier. It really doesn't matter. Okay, but I could get 4 minus pi over 2 pi minus 4, or yeah, whatever, 2 pi minus 4. It doesn't really matter how you want to write it, but this is equal to y bar. So where's our center of mass? Our center of mass is at 0, 4 minus pi over 2 pi minus 4. Now, that 4 minus pi and 2 over 2 pi minus 4, like, well, what the heck is that thing? Well, just plug it into a calculator. Okay, so I'm going to plug it into my calculator here. Okay, and it should, if I'm lucky, this should be a number between 0 and 1. Okay, let's keep our fingers crossed. Okay, so if I did it correctly, if it's a number that's bigger than 1, I have made a mistake. Okay, so 4 minus pi, okay, divided by 2 pi minus 4. Okay, and okay, I'm safe. This is 0 and 0.37, we'll call it 6. Okay, 0.376. Boom. Okay, so what's the point? What was the point of this whole thing? Okay, this is the center of mass. Okay, the center of mass for what? For this wire. Okay, where's the center of mass? Well, center of mass is located at 0.376. So that's about a third of the way up, right? So if I were to, okay, kind of attach, you know, maybe weld an infinitely small piece of wire to this, I could balance the whole thing at that point. Okay. It would be the balancing point. Of the wire. Okay. Okay. Whew, that was good. That was a good problem. Number 3 there. Let's keep going. Okay, let's keep going. We got another hour to go. It's good stuff. Okay, the line integral. With respect to x. Okay, is c f of x y dx. Okay, you're like, okay. But that's a line integral with dx. Well, with respect to x, right? So not a ds this time, a dx. Interesting. Okay, but we still have to have a parametric form of this. Okay, and how would we change this to a parametric form? Well, it would be over c, okay, or we'll say from a to b, okay, of f of x of t, y of t, and dx. Well, dx would be dx dt, right? If it's dx, but I parameterize this in terms of t, then dx becomes dx dt, right? Which is just x prime of t dt, okay? X prime of t dt. I should have an arrow here, not an equal sign. Okay. Okay. Similarly, okay, with respect to y, okay, we're going to go c to d, okay, of f of x comma t, y comma t, okay, y prime of t dt. This is if I want to isolate these. Okay. Now, sometimes it's easier to talk about the pieces of a line integral without doing the whole thing at that once. Okay, let's isolate the line integral with respect to x. Let's isolate the line integral with respect to y, and then bring them together. Okay, it's just easier to work with at times to do that. So we're gonna say that p of x is the line integral with respect to x. Oops. What happened there? Okay, let me get rid of this. Go back. There we go. What the heck? this thing. Whatever, I don't care. That is going to bug me. Where's the whiteboard? Meeting controls, whiteboard. How do I access my whiteboard? Disable, 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 disable. Okay, well, whatever. Okay, there you go. Okay, sorry about that. Okay, so y, okay, with respect to y. And so again, we want to take these individually, okay? So we're going to say that the integral with respect to x, we're going to call p of x, y, dx, okay? And then the integral with respect to y, we're going to call q of x, y, dy, okay? Okay, and so we're going to say that this is c, okay, of p of x of t, y of t, x prime of t, plus q of x of t, y of t, y prime of t, dt. Okay, and then I could split that into two different separate integrals if I really wanted to. Okay, that's not necessary. Okay, let's evaluate. Let's go into number 4 here. Okay, evaluate the line integral c of y squared dx plus x dy, where c is the line segment from -5 to -5, -3 to 0, 2. Okay, so we need to parametrize, okay, okay, a line segment. How did we parametrize a line segment again? How did we make a parametric form of a line segment? And again, this is in 3 space. This isn't not in 2 space. This is in 3 space. What was a line in 3 space? How did we parametrize a line in 3 space? Oh, with a vector, right? With a vector representation of that line, right? We used vectors to do that, right? The line segment. And if you recall, the form of a line segment in 3 space was r of t is equal to 1 minus t times r naught, okay, plus t times r1. Okay. That's a line segment, okay, represented in 3 space with vectors, right? In 3 dimensions, we have to have a vector representation of a line. Okay, we have to use vectors to get a representation of a line. And in this case, it's a it's a line segment. And how is this going to create my line segment? Because if I plug in 1 here, then 1 minus 1 is 0. That just becomes, okay, R1. Okay. And then if I plug in 0, it's 1 minus 0 plus 0 R1, and the R1 drops out, and I'm just left with R naught. So this tells me that I'm going from R naught to R1, okay, R sub 0 to R1, because as t goes from 0 to 1. As t goes from 0 to 1, I'm going from R naught to R1. Okay, so R naught to R1 as t goes from 0 to 1. Does that make sense? Okay, because one's going to get canceled out and the other one's going to get canceled out depending upon where I'm at 0 and 1. It's just saying, hey, I'm on this line segment, okay, and that is my line, okay, in the XY plane, okay, but I'm going to have to parameterize this in 3 space, even though it's on the XY plane, and there's only 2 components for R naught and R1. I still have to put it in parametric form, okay, because it is going to be represented in 3 dimensions. It just happens to be in 2 dimensions right now, okay, but it is in 3 space. I guess that sounded kind of confusing, but just know that this is on the XY plane, but there really is a Z component as well. Okay, this is the XY plane. Okay, so when we parameterize this thing, we're parametrizing it with respect to 3 dimensions. Okay. Okay, so let's do that. Let's parameterize this thing. So R of t is equal to 1 minus t times R naught. Well, what's R naught? R naught is my first vector, the vector from 0, 0, right? It's the vector from 0, 0 to -5, -3. Well, that's just this vector. And R's are vectors. Okay, so that's -5, -3. Okay, plus t, okay, times R1. Well, what's R1? It's 0, 2. Okay. Okay, so let's distribute. We get -5. Okay, we're going to distribute the 1 minus t here. So we get -5 plus 5t, comma. This is -3 plus 3t. Okay, plus, let's distribute the t. And I get 0, comma 2t. That's a vector. I'm going to add the vectors together. Okay, so this is -5 plus 5t plus 0. That just becomes 5t minus 5. Okay. And then this is -3 plus 3t plus 2t, right? We're going to do this one. And so that just becomes 5t minus 3. Okay, so that's my, and so what is this? This is, oh, look at that. That's x and y, right? That's x and y in terms of t. So this is x sub t, and this is y sub t. Oh, well, that's nice. Okay, so we're going to want to integrate, okay, our line integral here for y squared dx plus, okay, x dy, right? Those are going to be our line integrals, okay, with respect to x first, and then with respect to y. Okay, so y squared is with respect to x, and x is with respect to y. Okay, so this is going to be y of t squared x prime of t, right? dt plus, this is going to be x of t times x prime of t, right, dt, or sorry, y prime of t, my bad, y prime of t dt. Okay, cool. Okay, and so what is t going from in this case? Well, let's plug in r of t here, right? R of t. Our limits of integration, we said, were from 0 to 1 because that's how we set up a line segment, right? This is a line segment. And t is going from 0 to 1. And again, you can convince yourself of that by plugging in to the vector, right? These endpoints. Plug in 0. Well, what's 5 times 0 minus 5? That's just negative 5. What's 5 times 0 minus 3? That's negative 3. That gives me my first vector, negative 5, negative 3. That gives me my starting point. What about the other one here? Plug in 1. That's going to give me 0 and 2. Well, that was my ending point. That was the vector that gives me my ending point. So that does work. So t is 0, 2. What was y of t? Well, y of t is 5 t minus 3 squared. What's x prime? Well, what's the derivative of x? Right? What's the derivative of x here? Isn't it just 5? Because what's x of t? It's 5t minus 5. So what's the derivative of x? It's just 5. dt plus 0 to 1. What's x of t? Well, that's 5t minus 5. What's the derivative of y? Wasn't that just 5 again? Because wasn't y of t 5t minus 3? It's just 5 dt. Okay, I'm going to square this out to make it kind of nice. I'm going to pull the 5 out in front as well. 0, 1. This is going to be 25t squared. This is going to be 1530 negative 30t, right? Okay, and then this is plus 9. Okay, this guy over here is 5, 0 to 1 of 5t minus 5 dt. Let's integrate. This is going to be 25 thirds t cubed minus 15t squared plus 9t from 0 to 1, all multiplied by 5. Okay, plus 5 times, this is going to be 5 halves t squared minus 5t from 0 to 1. Okay, so let's clean this guy up. Again. Okay, if I plug in the 1s, we just get the numbers. And if I plug in the 0s, we just get zeros. So that's kind of nice. So this is 5 times 25 thirds minus 15 plus 9. Okay, plus, this is going to be 5 times 5 halves minus 5, right? Okay. Okay, let's clean this up. This is going to be 25 thirds minus 45 thirds plus 27 thirds times 5 plus 5. This is going to be 5 halves minus 10 halves. Okay, so this is negative 5 halves times 5, which is negative 25 halves. Okay, this is going to be 25 minus 45 is negative 20, plus 27 is 7. So this is 7 thirds times 5, which is 35 thirds. So this is 35 thirds. Bring this over. This is minus 25 halves. Okay, so this is going to be 76 minus 75 sixths, which is negative 5 sixths. Boom. Done. Good times. Okay. Line integrals in 3 dimensions. Okay, we're going to do line integrals now in 3 dimensions. Okay, so again, extremely similar to what we've already done. We're just going to add a 3rd dimension. It's really nothing to worry about. Okay, instead of c over xy, it's c over xyz. So f of x, y, z. We're just going to have to parameterize in terms of x, y, z, but we can still parameterize this in terms of one variable t. Okay, ts is equal to a to b of f of x of t, y of t, z of t, square root. I'm just going to put x prime of t, sorry, x prime of t squared, y prime of t squared, z prime of t squared. Okay. And then there's a dt at the very end here, dt. Okay, I couldn't squeeze it in. Can I? Oh, yes, I can. Never mind. It's my screen that was off, not my paper. Okay, dt. There we go. Okay. Now, one thing that I want to talk about right now is writing it like this: x prime of t squared, y prime of t squared, z prime of t may help you understand why we could do the last step that we did way back here when we talked about taking these things with respect to x's and with respect to y's individually. Because what would I do if I'm just integrating the line integral with respect to x? Wouldn't this really be the square root of x prime of t squared? And wouldn't that just get me back what I originally have? Does that make sense? Like if I'm integrating this just with respect to x, then wouldn't I have the distance of x, right? Just like of x prime, right? That's the, well, isn't that just going to be the absolute value? Isn't that just a one-dimensional distance, which is just the absolute value of, right, that thing? Well, we don't really do the absolute value, but it kind of undoes each other. Okay, so yeah, so that's kind of the idea behind that. Okay, although the sign does matter. Okay, because it's displacement, not distance, in that case. But you don't really need to know that. Just memorize the formula. Okay. So I mean, sometimes it's good to know why we're doing what we're doing. Okay, but I don't want to get too technical. Okay, number 5. Okay, evaluate. Okay, the integral of c of y sine z ds, where c is the circular helix x equals cosine t, y equals sine t, z equals t. Okay, from 0 is less than or equal to t is less than or equal to 2 pi. Okay, so what does this thing look like? Just a rough sketch. Remember, this was the coil that went up, that helix, right? Okay. Okay. Okay, looks like a spring. Okay, it's coiling up. Okay, so what do we need? Well, we need to know what x prime is, we need to know what y prime is, and we need to know what z prime is. Okay, x prime is going to be negative sine t, y prime is going to be cosine t, and z prime is equal to 1. Okay. Okay, so we want to take our line integral 0 to 2 pi of, okay, of y. Well, what's y? What is y? How do we parameterize y? Okay. Okay, y is sine t times sine z. Well, what was z? Well, wasn't that sine t as well? Yeah, sure. Okay, what is the arc here? What is the arc length in 3 dimensions? What's the arc length in 3 dimensions here? Well, it's just negative sine t squared plus cosine squared t plus 1 squared. Well, this thing becomes 1. 1 plus 1 is 2. And so this just becomes radical 2. This whole thing goes to radical 2. Okay. I'll pull that radical 2 out in front. I get 0 to 2 pi of sine squared t dt. And again, how are we going to deal with this? Again, that's our half angle identity, right? So a lot of half angle identities here in Calc 3. Okay. Okay, so this is going to be 1 minus cosine 2t over 2. Okay, we've already integrated this before. This is just 1/2 t minus, or sorry, is it minus or plus? It's plus 1/4 sine 2t, right? Is that right? No, it should be minus. Because if I take the derivative of this, yeah, it should be minus. Okay, and that's going to be evaluated from 0 to 2 pi. Okay, with our radical 2 out on the front. Okay, this is going to be 2 pi over 2, which is just pi, minus 1/4 of sine 2t times, sine 2 of 2 pi, which is 4 pi. Okay. Okay, and then minus, okay, 1/2 of 0 minus 1/4 of sine of 0. Okay. Well, what's the sine of 4 pi? 0. What's 0? 0. What's the sine of 0? 0. The only thing that survives here is the pi, right? The pi and the radical 2. So this is pi radical 2. That's it. Okay, and so we evaluated this. Okay. This helix, one cycle of the helix. Okay, so the picture really should look like this. It should really just be one cycle. Okay, it should just be one cycle. Okay. Okay. So let's now talk about line integrals in vector fields. Okay, line integrals in vector fields. Okay, let f be a continuous vector field defined by a smooth curve C given by a vector function okay, R of t. Okay, that's a vector function, R of t. Okay, semicolon. A is less than or equal to T is less than or equal to B, period. Then the line integral of f along C is okay, W equaling C f dot dr equals A to B, okay, of f of R of t dotted with, that's a dot product, not multiplication. Okay, R of R prime of t dt, okay, which we call the line integral of C of f dotted with t, okay, or our tangential, okay, our tangential vector, okay, because remember, again, like if we have a curve, right, and we have, say this is R of t at this point, right, these are our space curves, okay, and so we have a curve defined by a vector valued function, okay, then, okay, R of t, or sorry, R prime of t, okay, is that derivative, okay, or tangential, okay, derivative there, okay, it's our tangential function, our tangential vector, okay, over this curve, this curve integral, okay, or line integral, okay, and that's ds. Okay, W is kind of interesting. What is, why W here? Well, because F, really, the big F here refers to force. Okay, and T is with respect to distance. Okay, and so we have force times distance. Okay, force dotted with distance. And so what's force times distance? Well, yeah, force times distance is work. Okay, yeah, thank you, Faraz. Okay, it's work. Okay, so it's work done. So we can find the work done by pushing a particle through a medium over a pathway. And that pathway doesn't have to be linear in this case. That pathway can be curved. Okay, so this is how we get the work done over a curved pathway. Okay. okay, in something called a force field. This is a force field. Okay, it's not just a force, it's a force field. It's a field of force. It's the vector field. It's everywhere in this space. Okay, this spatial region in the XY plane. Okay, it tells me what the forces are acting on a specific at a specific point. Okay, so for example, you know, if we have a vector field, right? So here, maybe the forces are pushing down and they're not too big, okay, for that XY point. But over here, okay, maybe the forces are going down like this and they're really big, okay, really big force, okay? So again, try to think of this like, you know, water, you know, or air, right? Maybe if a particle is over here, it's just being blown in this direction. Okay, it's being blown in this direction. Okay, just a little bit, and then when the molecule of air hits this, maybe there's a first fan. I don't know how to draw a fan, but whatever. There's a first fan over here pushing the air over, but then there's a huge fan pushing the air down, right? So when the air moves over, when the particle moves over here, it's just getting a little bit of push, but when it hits over here, it gets a lot of push. And so that force field tells me how these molecules of air are flowing in this room. Okay, so again, so this is the force field, okay, and so this is the force that's being applied to every one of these specific points, okay, in this vector field. And again, maybe it's a small vector here. Once it enters this flow, though, it becomes a large vector, right? So they're all little vectors over here until they become large vectors over here. And so it just, you know, it's like, oh, we're going to shoot this particle over here, and then as soon as it hits the flow of the fan here, okay, then it starts moving and grooving, and maybe this is in, you know, some sort of chamber, right? So it's in some sort of enclosed chamber, and you're saying, well, this is how all of these particles react in this dynamic. Okay. Okay. So let's do our last example here, because I'm running out of time. I actually have a half hour, but that's okay. Okay, find. You're like, no, you don't. You're like, I'm done. You have 10 minutes. Okay. I'll do what I can. Okay, I will do what I can. Okay, find the work done by the force field f of xy okay equals x squared I minus xyj. Okay, now that freaks you out, the i's and the j's, just turn it into a vector. Okay, don't worry about the i's and the j's. Okay, okay, along, find the work done by the force field of this. This tells me that how the forces are being acted for every x and y value in my plane. Okay, what are those vectors? Okay, along in moving a particle along the quarter circle You're like, oh, we're moving along a circle again. Yeah, exactly. Go figure, right? Okay, along the quarter circle, okay, and we need a vector valued function for a circle. What circle is it? It's just the unit circle again, okay? But we want that to be in as a space curve, okay? And so a parametrized vector, because we're dealing with vectors, right? So how would I parameterize the space curve as a vector? Well, it would be cosine of ti plus sine of tj, right? Wouldn't that be that, right? And so again, if the i's and j's mess with your head, that's fine. Just go cosine t sine t. This is along the unit circle, okay? And what's t going from? T is going from 0 to pi over 2, okay? Okay, so what does this tell me? It's telling me that the work done is equal to force dot dr, okay? Force dot dr, okay? The force field dot with dr, okay? So, and what is that? That's x and y's. But again, I have to put this in terms of r's and t's. Well, what is x? X is equal to, or sorry, not r's and t's, just in terms of t. What is x equal to? Well, x is equal to cosine t. What's y equal to? Sine t, right? Okay, so what's my force field going to be equal to? Well, it's going to be 0 to, I got to translate this all into t's, 0 to pi over 2. Okay, what's f? F is, okay, going to be x squared, comma, negative xy. Well, this is going to be cosine squared t, comma, right? Again, these are vectors. Cosine squared t, comma, this is negative cosine t sine t, right? Dotted with dr. Okay, well, what the heck is dr? Well, dr is the derivative of r of t. It's just r prime of t. Okay, so what's r prime of t going to be? Well, we kind of already, figured that out because, well, r prime of t is just the derivative of x of t, y of t. Well, what's the derivative of x? Well, the derivative of x is, okay, so dr is just r prime of t, right? R prime of t, okay, which is again is a vector. This is negative sine t cosine t, okay, and then give myself a little extra room, dt, okay, oh, and this is cosine t. And now what are we going to do? Well, we're going to do a dot product on this, right? Remember how to do the dot product? Okay, so we're going to multiply and add. So this becomes negative cosine squared t sine t plus negative, oh, look at that. It's negative cosine squared t sine t. Again, dt. Okay. So what is this? We have the two of the exact same thing. So isn't this negative 2 cosine squared sine t? Right? From 0 to pi over 2 dt. And this is just an easy u sub. U equals cosine t. Right? du equals negative sine t dt. That takes away the negative, the sine t. Okay, that I want to bring that 2 out in front. So this is 2, okay, times the integral of u squared. Okay, I do need to translate my limits of integration. What is the cosine of 0? Well, that's 1. What's the cosine of pi over 2? Well, that's 0. Okay, so I've got 2 times, this is going to be u cubed over 3, evaluated from 0 to 1. Right, so this is going to be 2 times 0 minus 1/3. Okay, which is negative 2/3. And that is the work done, okay, over this vector field. Now, why is it negative? Okay, why is it negative? Well, because it looks like this, okay? Don't mess with me right now. Not in the mood for that. There we go. Okay. Okay, so it looks like this. Okay, what do we got? We've got a quarter circle here, right? Okay, we've got a quarter circle here. And where are we going on that quarter circle? Well, we're going from 0 to pi over 2. So we're traveling along this quarter circle from 0, theta equals 0, okay, to pi over 2. So we're going from 0 to pi over 2, right? So we're going that way. But what is this telling me that the work is negative? It means that the field, the force field here, which maybe the force field is like this, and then over here is like this, and then as we go down, it's going to be pushing everything down, right? For any xy value, it's going to be pushing this down, right? You see how the force field impedes our direction, right? So the force field is impeding the direction that the particle is moving. And so that's why the work is negative. Okay, the force field impedes the direction of movement of the particle along C. Okay, we're good. Look at that. We got you out of here by 10 o'clock. Okay, if you have any questions, I will be sticking around for 15 minutes. I actually, well, I'll have office hours right now if you want. I have a meeting at 11 o'clock, so if you have questions on the homework, I will be here for the next hour. I'll just leave this open. So just, yeah, let me know. Yeah, okay. Otherwise, at this point, you're dismissed, and I will upload this lecture to YouTube, okay, as soon as I stop sharing. Okay.